Okay, so let us teach a little bit, so to finalize this section, implicit differentiation. Of course, the teaching part is finished, but I want to solve a little bit more interesting problems. So, I don't know how much you remember. Hopefully you haven't totally forgotten everything. But let me start with an example in the book so that if you have forgotten, at least I can refresh your memory. So there is a problem in the book. In this hard copy it is 5013, okay? But I don't know in the electronic version if the number is the same or not, but let us assume that this is the same. Exponent 5, yes? It is mentioned that an ellipse is described by this equation. So you don't need to be worried why this equation describes an ellipse, but that is given to you. You can take it for granted. Is equal to 1. So this describes an ellipse. You will study that in the university later. But they ask you find an equation for the tangent to this ellipse at this point, square root of 3 and 2 on the ellipse. Okay? So we want to do that. So you see that this is an implicit function because x and y are mixed together, and then you want to find an equation for the tangent line. So it means that you have to find the slope of the tangent line. So it means that I have to differentiate. But because this is not an explicit function, I have to use implicit differentiation. I would recommend you first of all try to simplify these fractions a little bit. So this becomes x to the power of 2 divided by 4 plus y to the power of 2 divided by 16 is equal to 1. To get rid of all fractions, let us multiply everything by 16. That would be easier, I think. So this becomes 4x squared plus y squared is equal to 16. So I multiplied everything by 16. So this is easier for you to see. Do you know that if this 4 is not there, that's a circle? So that means that actually you see a symmetry. Yes, asymmetry between circles. So you see here 2x squared plus y squared is equal to 16, so it cannot be, of course, a circle because you have a factor of 2 here. Anyway, this describes an ellipse. Let us check this point is really on the ellipse or not. So I have to replace x with the square root of 3, which becomes 3 times 4 is 12, and then 2 to the power 2, 4 plus 12, 16. Yes, so that point lies somewhere on this ellipse. And then you want to find the derivative, but you have to start differentiation. So let me start from scratch again. So what I do, I differentiate both sides with respect to x. But the derivative of this one is simply 8x. The derivative of y squared, that's the whole point. It is not just 2y, because y is assumed to be a function of x itself, so it becomes 2y, but multiplied by y prime. And the derivative here is 0. Now I want to find the derivative y prime, so I move minus 8x to the left, it becomes minus 8x, and then divide by 2y to make y prime alone. So if I simplify that, y prime is minus 4x divided by y. Of course, in division, I am assuming tacitly that y is not equal to 0. And that is not the case, because here I am interested in this one, at this point. Okay, so then I want to find the k-value. So the k-value of the tangent is equal to what? Instead of x, I put the x-coordinate of the point of tangency, which is the square root of 3, and then the y is 2. So it becomes minus 4 square root of 3 divided by 2, which can be simplified to minus 2 square root of 3. So now I have the k-value, and I have the point, and I write the formula for the tangent line. Y minus y node is equal to the k-value I found, x minus x node, yes? So this means that I have y minus y node, which is 2, equals to k value minus 2 square root of 3, and then I have x minus the square root of 3. If you want, you can also simplify it a little bit. So y becomes equal, I multiply this in, so it becomes minus 2 square root of 3x. This becomes positive 6, but I move minus 2 to the other side, it becomes positive 8. So that is an equation for this ellipse. Might be that's also good to check it on GeoGebra. Okay, so I go here. Let us see if you can also see that, but unfortunately this curtain is not working, or is it? Let me check. Okay, so what was my ellipse? So the ellipse was, it's in the book, so let me just do it here. So I have x over 2, yes, and then a squared, totally squared, and then I have plus y over 4, and then I have totally squared is equal to 1, yes. So, and you see this is your ellipse, okay, and then I try to find that point, square root of 3 and 2. So if I want to find that point, let me call it T, point of tangency, and I have a square root of 3. Let me use the keyboard here, square root, oops. So a square root of 3, and then I have outside that 2, yes. Okay, so that, as you see, this blue dot is actually that point, yes? And then I want, so you see that, of course, there are points at which y is equal to 0. So it means that for those cases, the derivative is not defined because the denominator vanishes. But at this point, that is okay. I don't know if GeoGebra is possible for us to do that or not. So I use this tangent feature and I just click on it. And on the curve, hopefully I get my tangent line. So this is predicted by GeoGebra to be the equation, yes? So momentarily I can actually remove that. Show object, no. So what I got, do you remember y equals to minus 2 square root of 3 and then times x, if I remember, plus 8. Yes, this is what I got. Yeah, that's correct. So that is exactly that line that we found. So that's the meaning of implicit function. So it is not a function. By the way, let me repeat that. Why this curve, why this ellipse is not a function? You remember, because if I draw a vertical line, for example, here, it will intersect the curve more than one point. So this means that this cannot represent a function, but of course, talking about the tangent to the curve is still a sensible and meaningful question, and then we were able to answer that question, yes? Okay, so that is hopefully a refresh of your memory. Okay, so I will go back and try to solve a little bit harder and more interesting problems, okay? Okay, so let us choose some problems from this book. Something, but I think it is interesting. Let us talk about that together. So there is a problem in this calculus book written by Adams, which is of course used also at KTH. So this function is given, this not function, this implicit function is given to you, x plus y to the power of 5 plus 1 equals to y plus x to the power of 4 plus xy squared, and this is written in this form. You are supposed to find the second derivative. They have written it in Leibniz notation, but at which point? At the point 1 and 1. Okay? So this is the question. So far we learned how to find the first derivative for implicit function, but I don't think it is a very big leap if you just want to go to the second derivative yourself. I think you can do it, okay? Or at least you can tell me what to do. First of all, do you think that that point is on the curve or not? I cannot call it a function, but I can call it a curve. 1 and 1. I put 1 and 1 instead of x and y. The left-hand side becomes 3, and on the right-hand side I also get 3. So that's okay. So this 1 and 1 is of course there. Okay, can you tell me what to do? I want to find the second derivative of an implicit curve. So what should I do? What is the most natural step? The first derivative, yes? So we do the first derivative. So what happens here? I take the derivative from both sides with respect to x. So this becomes 1 plus 5y to the 4, but remember, y prime. Yes? And then the derivative here is 0. The derivative on the right-hand side is y prime. This one is 4x cubed. But can you tell me what should I do with this one? What rule is applicable here? It's a product rule, yes? X times y squared. So it becomes the derivative of x, which is 1 times y squared, plus this one multiplied by the derivative of the second one, which is 2y, y prime. So it becomes 2xy, y prime. Okay, but I am not allowed to put these numbers right now, because if I put this one, y prime becomes a number, and of course y double prime becomes 0, so it's not reasonable, yes, because I have to have my derivative as a form of a function to go to the second derivative. So this means that I take these 3 terms into account and move them to the left-hand side, factor y prime out. So this becomes 5y to the 4 minus 1 minus 2xy y prime, and then this one is left alone here. I move all of them to the right. So 4x cubed plus y squared, and then minus 1. Assuming that this is not 0, okay, we can also double check. If I put 1 and 1, of course it might be there are some points for which this is 0, but at least I am on the safe side if I want to talk at this point. Because at that point this coefficient is no longer 0. So I find y prime. So y prime is 4x to the power of 3 plus y squared minus 1 divided by this expression. So 5y to the 4 minus 2xy minus 1. So this is my first derivative. Okay, and then what I have to do, I have to calculate one more derivative. So that is a little problematic, okay? They have mentioned that you have to calculate this using the computer. There is a mouse sign icon next to it. But let us do it with hand, okay? If we cannot do that, then we can just go back to the calculator or something. But y double prime, at least I think you can do it, yes? Okay, y double prime is the quotient rule. So it becomes the derivative of the numerator. So 12x squared, yes? And then plus 2y y prime, which is minus 0 times the denominator. Yes? And then minus the derivative of the denominator, which is 20y to the power of 3, but multiplied by y prime. Okay, let us do as much as we can in our head. So if I want to differentiate this, the derivative of the first one is minus 2 times y, but plus 2x times the derivative of y. So it becomes minus 2xy prime because this minus sign goes for both of them. This one multiplied by the numerator. Yes, I think that's the reason they ask why you have to calculate this, yes? And then the denominator is squared. Okay? If I ask you to find y double prime, then this is horrible because then you have to replace every appearance of y prime and put this expression there. And then it becomes really messy, okay? Might be that's the reason they have put that icon, but I don't believe we need that icon, yes? Because my goal is to calculate the second derivative at the point. So I put the numbers here and I find y prime as a number, yes? So what will be y prime at that point? So x and y are both 1. So 4, 1, minus 1, it's 4. And the denominator is 5 minus 2 minus 1 is 2. So it is simple. It is y prime at that point is 2. Not always, but at that particular point the slope is 2. And then I come back here and try to calculate this. It is not hard, by the way. So instead of x and y, I put 1 and 1, but instead of y prime, I put 2. Then I get the number, yes? So what happens here? It becomes 12 and 2 times 2, 4, 16. And then I have here 5 minus 2 minus 1, which is 2. Minus, this becomes 20 times y prime is 40, minus 2 times 2 is 4, and then multiplied by 4 plus 4. Oh, sorry, I forgot to put a power of 2 here. And then divided by this expression to power 2, which is 2 to power 2. And I don't think really we can simply calculate it, isn't it? So this becomes 32. So 40 minus 2 minus 4 is how much? Is 34. Multiplied there, it becomes 128 divided by 4. Am I right? Yes.
136.
Yeah. By the way, I didn't need to do these things, yes? Because I can divide everything by 4, then 16 over 4 is 4 times 2 is 8, and this 4 and that 4 are gone. 40, 38, 34. So it should be minus 26. Yes, so apparently I don't know if that's unfortunately the answers are not given unless they are odd numbered. And okay, this is odd numbered. We can check the answer to see if we have done it right. 2.9 25 minus 26. Yes, that's correct. Okay. So I don't know, it didn't need that computer to come to help us, yes, because it was easy to do. Okay, but let me try to understand this a little bit better. Can you tell me, you see that I calculated the derivative, at that point it becomes 2. And when I calculate the second derivative, by the way, this is not the second derivative. The second derivative is this one. This is the second derivative calculated at that particular point. And it turns out to be negative. What is the geometrical interpretation for that negative value? I think the students who had Math 3C with me realize what is the idea of the second derivative. It has something to do with concavity, yes, do you remember? If the second derivative is negative, it is like an upside down bowl, and if the second derivative is positive, it means that it should be upside, it should be a normal bowl, but of course around that particular point, yes? So I don't know, could you guess what happens? Let me try to visualize this using GeoGebra and try to understand what is really happening here for this negative number. So my prediction, our prediction is actually that the concavity of that curve, whatever that is, at that particular point should be like an upside down bowl, okay? And then what the tangent is at that point, it is positively sloped. So can you guess what will happen around that? It is probably complicated to understand the whole picture, but something is more or less clear for us, hopefully. If this is 0.11, first of all, I know that I have a curve. The curve has a tangent with positive slope. This is on the one hand. On the other hand, we predicted that it should be like an upside down bowl, okay? So what does it mean? Because when I say that slope 2 is something like this, yes? If I give 1, it gives me 2. So this means that this is my slope 2. So this would be somehow my tangent line. This is my tangent line. But if I draw it like this, then the second derivative should be positive. Because the second derivative is negative, so we predict that something like this happens. So around that point, something like this happens. By the way, this is the trick that computers use to draw the implicit function, something like that. So you can, even though you don't know the big picture, but you can understand it locally, point by point. So you can just connect them to make the big picture, okay? But let us see how GeoGebra shows this to us, okay? I don't need anything. The numbers are 2 and minus 26. This is easy to remember. And the function, I will write it from the book again, okay? Okay, so I think it would be better if I can get rid of these. We don't need them. And let me try to... It's a little bit exciting to see how the curve looks like, yes? Are you excited also? Should be. Okay, so x, I would write x plus y to power 5 and then plus 1 is equal to y plus, oops, I'm writing everything up there, yes, sorry. So x plus y to the power of 5 and then we go down and then plus 1 equals to y plus x to the power of 4. Yes, it's already interesting. So I don't know what's happening. I couldn't predict that. It's why it is. Okay, that's only the. So do you understand what's going on? Plus xy squared. Let me x y squared. Okay, so I don't really understand. So this is, did I type it correctly? So x plus y to the power of 5 plus 1 equals to y plus, that seems to be correct. I don't know why GeoGebra does this, and Control Z doesn't work here. Do you know how can I undo? Here.
Yeah, no, the undo.
Undo.
Yeah, the one with the arrow that's curved. Right there.
No, undo on the. Does it work here? It doesn't work on the writings, you know. It undo what is okay. But let me just type it again. It's better. X plus y to the power of 5, and then plus 1 equals to y plus x to the power of 4. This appeared again, okay? Plus xy squared plus x times y squared. Anyway, that's a very nice shape, isn't it? Okay, so that is the curve. But let me just find that point here as well. Point of tangency, let me call it, or whatever, is equal to 1 and 1. I don't know why I typed this, I'm sleepy. I was working on a problem, I couldn't sleep yesterday. Okay. So, now, this is tangent. Okay, but could you really predict this is happening? Because the slope is predictable. Yes, the slope is positive. If I take this tangent line and I ask GeoGebra to draw the tangent line for us at this point. No, that is also understandable. Why? Because GeoGebra draws all possible tangents that passes through that point as is and are somehow tangent to the curve. So it doesn't care about exactly that point. Yes? So it is not very helpful. But which one was our case? The positive slope one, yes? So this is exactly passing through that point because you know that the other lines are passing through T, are tangent to the curve, but that is not the point of tangency. T is not the point of tangency for them. Okay, so this is not a good idea. So let me get rid of it. But could you see that it is upside down ball or something? Might be not clear, but if I zoom in, it probably should appear at some point. Yes, I still believe that that is true, you see. So I hope that you see, if I draw this tangent line, the curve is below the tangent line, at least locally. Okay? So you see that we were able to predict something about that locally. And that is, by the way, very important because mostly in science we don't care about all the points on the curve. For some reason we become interested at some particular point and region on the curve. So it is actually a very strong tool to predict what's happening locally around that point. Okay? I think I will also solve another one. This is also interesting here. So let me just close this. Okay, there is another problem. I think it is good. I want to solve it without using GeoGebra at all. But then I will come back and show what is going on as a picture or whatever. So they have put an exclamation mark for this question, meaning that probably it is hard. I don't know, but it is not that hard, I think, but let us try. Understanding it might be a little bit hard. So they have given you two curves. One of them is x squared plus 2y squared is equal to what? Is equal to 2. Again, you will see later this is also an ellipse, but this would be a horizontal ellipse rather than vertical ellipse. And then another curve is given to you. It's 2x squared minus 2y squared is equal to 1. Later you will see that this becomes a curve which is called hyperbola. Okay, so hyperbola. But you forget about the name and about the shape. We will see it later. But what you see two implicit curves. According to the book, they intersect each other. Okay? You want to show that at the point that they intersect each other, they are perpendicular to each other. But of course, this is a little bit vague idea for you because if I tell you two lines are perpendicular, you understand what I mean. But what is the meaning of two curves to be perpendicular? It means that if you draw a tangent line to one of them at that point, draw a tangent line of to the other one, this angle is 90. I mean, sometimes people call about the angle between curves. When they talk about angle between curves, it means that at the point of intersection, draw a tangent line to one of them, draw a tangent line to the other one, and measure the angle between tangents rather than the curves, because that's meaningless to talk about. If this turns out to be 90, then you say that the curves are perpendicular. Okay? So that is something we want to show. We want to show that these two curves, whatever they are and whatever they are called, hyperbola, yes, they intersect and they are perpendicular at the point of intersection. So how should I do that? I intentionally want to do it without any drawing because you really don't need drawing at all. So what should I do? First of all, what is the first step? Tell me. What is the first step? The first step is very natural. Please say to me what to do immediately.
Find the direction.
No, not yet. That's also good. It might be that's also can be called the first step. But what?
The intersection.
The intersection point, because I need to know the intersection points, okay? So I set up a system, x squared plus 2y squared equals to 2, and then I have 2x squared minus 2y squared equals to 1. Then of course you need to focus your energy to be able to solve this system, which is not standard but very easy. What is your suggestion now? Yes? Add them, yes? Add them. If I add them, this one and that one are gone, it becomes 3x squared, it becomes 3, and then it means that x squared is 1, but you have to be careful, both of them are acceptable, plus or minus 1. So it means that these two curves probably will intersect more than 1 point. But how many points I want you to predict? Okay, so I put x here, but even positive or negative, it doesn't matter. When I raise it to power 2, it becomes 1. So this becomes 1 plus 2y squared is equal to 2. Then it means that y squared, I move 1 to the other side, 1 divided by 2. And then y becomes plus or minus 1 over a square root of 2. So this is the calculation I did it for you based on what you told me. But now I want you to interpret the calculation. So how many intersection points do you predict? That's my question for you. Because the calculation is there on the board, so you should be able to interpret it properly, yes? Yes, Elias?
I assume 4.
4, yes? There are 4 intersection points, yes? Because you say that x is 1 or minus 1. If x is 1, I put it there and solve, I get 2 values for y, for that particular x. Then I change my x to minus 1 and I calculate it again. Again, I get 2 points. So there are 4 intersection points. So it means that the intersection points are 1, 1 square root of 2, 1 minus 1 square root of 2, minus 1, 1 square root of 2, and finally minus 1 square root of 2. So there are 4 points of intersections. According to the problem, that they are perpendicular at all the intersection points. Okay? But I think if we can solve one of them, you can similarly show the other ones. Okay? So now let us focus on the positive ones, yes? Now, what you said is probably applicable. I have to calculate the derivatives. Okay? So the derivative of this one is an implicit derivative, so it is 2x plus 4y prime equals to 0. Okay, I want to find y prime, which I move minus 2x divided by 4y, which becomes minus x divided by 2y. Provided that y is not 0, but I'm not worried because y is not 0. Okay, so what is the k value? Let me write k value number. So this is an ellipse, so let me write k of ellipse, okay? It becomes minus x over 2y, which is, x is 1, over 2 times y, 2 over a square root of 2. So if you write it, it becomes negative square root of 2 divided by 2. So the k of ellipse at the point of intersection, not the k of ellipse, k of the tangent to the ellipse at the point of intersection is this number. I will do the same thing for this one, so it becomes 4x minus 4y, y prime equals to 0. Okay, what I do, I move this to the other side and divide by minus 4y, so y prime becomes x over y, yes? But then I also put that intersection point, so the k of the hyperbola, the tangent to the hyperbola, is equal to x, which is 1 divided by this number. So this means that the k of the tangent to the hyperbola is the square root of 2, yes? And then I want to show that they are perpendicular. So what I have to do, I have to multiply them, and the product should be minus 1, and it is, yes? So this means that KE multiplied by KH, I multiply this by that, so it's square root of 2 times minus the square root of 2 divided by 2, but this becomes exactly minus 1. So this means that, yes, they are perpendicular. So It was not that hard, deserving exclamation mark, yes. But it is understandable. Okay, so let us just try to check this using GeoGebra. It is good to know that hyperbola is not a closed curve. It's like parabola. Parabola is also open. There are no inside, outside. The same is true more or less for parabola, but there is a bigger difference between parabola and hyperbola. Parabola is one branch. Hyperbola consists of two branches. Yes. So let us also see that. How is it going here? Okay. So I think that's it. So I would stop here for. Let me also. Okay, I will stop here, so don't teach anymore. But the next topic is again differential equations. Unintentionally, I taught the first part of that for you, but I think if we have time, that is also good to go to the other part, which is the second order differential equations. That would be an also nice topic, so we will continue next time. Any questions? Yeah? Thank you.